Our group's topic is data-driven solutions to engineering problems, and this research focuses on the analysis and optimization of operating models for electric vehicles. After analyzing a variety of models and existing problems in the literature, the K-means clustering algorithms was finally selected and focused on the application of the K-means clustering algorithm in the EVs industry. First, a few words about the background of the study. With the growth of urban population and concerns about the impact of the environment and global warming, EVs has been promoted as an appropriate solution to improve urban transportation. However, there are still many challenges in applying electric vehicles in urban transportation. For example, the driving cycle in urban areas is significantly different from the other regions. The charging behavior of cars is irregular, and the external factors such as traffic and the weather add to the complexity of urban centers. Data analytics are therefore critical in addressing these issues by collecting and analyzing data on EV usage. We can develop a regional plan for charging and discharging, schedule specific maintenance in advance to avoid possible breakdowns, and interconnect with the grid. This will not only increase the share of electric vehicles in global energy consumption, but also extend the battery life, reduce operating costs, and promote the use of electric vehicles in urban transportation. In the literature review, we examine scholarly research on battery management systems, charging infrastructure, and smart grids over the past 5 years. In particular, the application of data science and machine learning techniques in this area has led to new ideas. K-means clustering algorithms has been widely used to analyze the energy efficiency of EVs under different usage patterns. For example, by analyzing charging behavior and energy consumption, different usage behaviors such as commuting, delivery, and travel can be classified for more precise energy efficiency optimization. In addition to the K-means clustering algorithm, other data analytic methods and uniques also play an important role in EV energy efficiency optimization, such as deep learning, big data analysis, or system diagnostic modeling, or machine learning models. Next, I would like to introduce our solution and simulation process. In this project, we use the K-means clustering algorithms to analyze the operating modes of EVs, focusing on two key variables, battery state and charging or discharging power. The specific specs are as follows. Data loading and processing. Load the EV operation data from the CSV file, filter out of the necessary value columns, and deal with missing values and other layers. Cluster analysis is to analyze the cleaned data using the K-means clustering algorithm to determine the optimal number of clusters to ensure the accuracy and the usefulness of the results. Result visualization is to create scatter plots and histogram to display the clustering results and the data distribution characteristics, and to identify different operating states through the distribution of cluster centers and data points. During the simulation process, we found that the operation modes of EVs can be categorized into three types: high discharge states, high charging demand state, and no variation or standby state. Through three modes, we can better understand the usage of EVAs and develop more effective energy efficiency management strategies. In the results and the discussion section, we summarize the shortcomings of existing research, such as data quality and access challenges, high computational resource requirements, and the limitations in research scope. Future research directions include data acquisition and processing, developing smarter automated data conclusion systems to ensure high quality and integrity of data. Model optimization and computational resource management, researching more efficient algorithms and models, and exploring edge computing and distributed computing techniques. Cross-regional research and diversity analysis, conduct cross-regional and multi-city empirical studies to analyze energy efficiency management strategies and usage partners in different environments. Multidisciplinary cross-research is to strengthen cross-research in disciplines such as intelligent transportation systems, Internet of Things, and machine learning, and to comprehensively utilize a variety of technological means to improve the overall energy efficiency of EVAs. Finally, through a data-driven approach, we can significantly improve energy efficiency management of electric vehicles and realize greener urban transportation.
Next, I will explain how to use Python for data analysis and k-means clustering. This could mainly include steps such as data loading, pre-processing, model training, and result visualization. We will explain each part of the code step by step and show how to execute and interpret the results. We first imported the required libraries, which include NumPy, Pandas, Matplotlib, and so on. These libraries are used for data processing, plotting, and machine learning respectively. This code defines a function load data from CSV that loads data from a CSV file. It first reads the CSV file and then extracts the columns of interest, SOC% and power. Next, we convert the data in these columns to numeric types and fill in the missing values. To handle outliers, we calculate the z-score and remove outliers with a z-score greater than 3. Finally, we return a data matrix that combines SOC% and power. This code defines a function k-means that plays the k-means clustering algorithm. We specify the number of clusters as well as the random seed to ensure reproducibility of the results. The function returns the cluster labels and cluster centers. The function plot clusters is used to plot the clustering results. We assign colors and names to different cluster levels, and then plot each data point and its corresponding cluster center. This allows us to visually observe the clustering effects. Now you can see the function plot histograms plots the histograms of SOC% and power. Through the histograms, we can see the distribution of the data. The function plot elbow and COHT determines the optimal number of clusters by the elbow method, and the COHT coefficient method. We draw two graphics to show the distribution and COT coefficient under different numbers of clusters. By observing these graphics, we can find the optimal number of clusters. Finally, we call all functions defined above in the main function to load their data. That means the optimal number of clusters. Apply clustering, draw graphics, and output the results. The whole process is clear and straightforward, ensuring that we can get reasonable clustering results and conduct corresponding analysis. Okay, let's run the code. We can see that this code draws three graphics in total, in which we use the elbow method and the COT coefficient method to determine the optimal number of clusters. As shown in the figure, in the elbow method graph, the distribution decreases as the number of clusters increases, and when the number of clusters is 2, the distribution decreases significantly. In the COT coefficient determining the optimal number of clusters, we performed k-means clustering on the data, and the results are as follows. In this scatter plot, we can see the distribution of two clusters. The purple dots represent priority discharge, and the yellow dots represent priority charge. The red X marks indicate the location of the cluster center. It can be clearly seen from the figure that the two cluster centers are located in different charging and discharging power regions, indicating that our k-means clustering successfully divides the data into two meaningful groups. At the same time, we also plotted histograms of the two main variables to further analyze the distribution of data. In this purple histogram, we can see that the state of charge data is relatively evenly distributed, showing the frequency of each interval. And in this yellow histogram, we can see the data distribution of charging or discharging power. The data is distributed in both the positive and negative ranges of power, which further verifies that the power range considered during clustering is reasonable. And next, let's turn our attention to console. We can see the information output by console. We get the center point location of each cluster, which are cluster center 1 and cluster center 2. The data points contained in each cluster are as follows. This group 0 and group 1. We can see that different groups have obvious differences in charge and discharge power. The data points in group 0 are mainly concentrated in the positive power interval, while the data points in group 1 are mainly concentrated in the negative power interval, which verifies our clustering results. Through this analysis, we successfully divided the data into two meaningful clusters and further verified the rationality of the clustering results through visual charts. That's all for our presentation. Thank you for watching.